Hi friends, good evening. Today we are going to focus in another coordinate system, that is cylindrical polar coordinates, right? So last class we seen what is spherical polar coordinate. There you seen to represent a point on the surface of a sphere, we require at least three coordinates, that is r, theta, phi. Similarly, to represent a point on the surface of a cylinder, here also we require three coordinates. That is actually cylindrical polar coordinates. For example, see, if you consider a point P, suppose this is a point on the surface of the cylinder, right? So you consider like this. This is a part of cylinder, right? Now this is a point on the surface of the cylinder, right? And then this cylinder must require a radius r, all right? So that radius vector should be defined to know about where this point, right? Now any point you take a radius is common. So by defining radius alone, we can say this is that particular point. To know about that, we require, suppose I draw a perpendicular to the base of this cylinder, right? So that base vector, suppose I make a position vector to that perpendicular, that particular position vector makes an angle phi, right? That phi also we require to define that particular point P, right? Then this particular point is located at any height, right? So we must require this height also, right? Now look into this diagram. If I consider this radius r and this phi and this height is z, right? Now look here, by defining this phi, z and r, the particular point, for a particular point we define these three parameters that is unique for that particular point. That means these three coordinate is essential to define this particular point that is unique for that particular point. All right. Now as we see in Cartesian coordinate system, all the axes are perpendicular to each other, all the coordinates are perpendicular to each other. Similarly, the unit vector in spherical polar coordinate system, r cap, theta cap, phi cap, right? That all are perpendicular to each other. Now see here, in which direction the radius of this vector is increasing, radius of this cylinder is increasing, this direction, right? So radius is increasing in this direction. So this is r cap vector, right? Now look into this figure, in which direction phi is increasing, right? This direction. That means phi is increasing. So if I draw a parallel in this direction, right? That means that is in this direction, right? If I draw, it is increasing in this direction. That means if I draw a tangent here, so this is the phi cap vector, right? And in which direction z is increasing, height we selected in this direction, right? About this axis, cylinder height is we taken in this direction, right? So that means z cap is increasing in this direction. Now look, like a x cap, y cap, z cap in Cartesian coordinate system, r cap, phi cap, z cap, all are mutually perpendicular to each other, right? Now in cylindrical coordinate system, we require this r, phi, z, right, to define this particular point, all right? So these are the r, phi, z, these are the cylindrical polar coordinates, all right? Now in terms of cylindrical polar coordinates, how we can define x, y, z, right? Alright. See, so this vector, right? Suppose this vector I am considering, this is r, right? This is radius vector because this radius, so this vector is parallel to this also radius. Now this is angle phi, then this is x-axis, so definitely this is r cos phi, adjacent side, right? And then this is y-axis, definitely this is r sin phi, alright? I made this r into two component, r cos phi, r sin phi. Then r cos phi is defining x-axis, r sin phi defining y-axis. Now what about z? Z is z only, right? Z-axis. So r phi z. So x I can write as r cos phi. Y I can write as r sin phi. Z is equal to z. Alright. Now what is the range of this coordinate we can choose? Right. So you can select a cylinder with any length, right? So z may vary from, so here if I choose 0 to infinity, any height cylinder you can take. So z you can select from 0 to infinity, alright? Or that is length of the cylinder is along z axis. Now radius, any cylinder with any radius you can, infinite radius. So r direction you can take as 0 to infinity, right? But look into phi. What is the range of phi? Phi can rotate like this is phi, then phi you can maximum you can take a 0 to 2 pi. Then phi range is 0 to 2 pi. Alright. So in cylindrical coordinate system, to locate a point, we require three coordinates, that is r, phi, z. Okay. So in terms of Cartesian coordinate system, x is equal to here r cos phi, y is equal to r sin phi, z is equal to z. Alright. Now as we discussed in other coordinate system, we require what is area element, volume element in cylindrical coordinate system, right? So let us go to see, before coming to area element and volume element, so let us do some range of r, phi, z in different situations, alright. See, here one figure given. So here x, y, z axis, one cylinder given, radius is given as r, then radius is varying from 0 to r, right? And phi is varying from 0 to 2 pi. So suppose phi is the full cylinder we considered, right? So phi value is 0 to 2 pi, right? And I chosen a cylinder with length L. So z is varying from z axis 0 to L, right? Now in this case, second case you see here I chosen a cylinder of length L. So here if I choose 0, to get L, this part should be minus L by 2. This part should be L by 2. Then only L by 2 minus L by 2, that is equal to L. Right. So Z is varying from minus L by 2 to L by 2. Alright. Phi no change. Phi is varying from 0 to 2 pi. Radius already given. Then R coordinate is varying from 0 to R. Now suppose you are considering this much part only, right? Then definitely radius R is given, then R is varying from 0 to R. But phi is this quadrant only we choosing the cylinder, right? One octant only we consider, right? So a quarter cylinder only, 1/4 part only I am considering. Then phi require this much value only. This is pi by 2, right? Then phi is varying from 0 to pi by 2. Alright. Then Z I chosen here a cylinder, 1/4 cylinder of length L only. Then Z is varying from 0 to this length is L, 0 to L. Alright. So in different kind of problems, we should select the values of the cylindrical coordinates, right? So to give limits, okay, in which from which value to which value this particular coordinate is varying, that is very important. Alright. Now let us see what is area element, volume element in cylindrical polar coordinate. See, for this I considered a cylinder as usual notation by increasing a small dr length, right? I considered a small change in dr, this direction, this is dr, alright, and a small height change dz I taken, and this this angle is phi, alright. So this angle change is a small d phi. So this is our radius, right? Definitely this arc length is r d phi, right? So arc length is r d phi, alright. So by increasing a small r dr, right, and a small length dz, and the arc length by increasing as angle phi, that is to d phi, right? Then angle phi is increasing as d phi, alright. Then by this increase you can see a small volume created here. Now, so this is the volume. What is this volume? That is area into width. Suppose this area, first I can write area element. What is area? dA is equal to, so this length into breadth, that is dr d phi dz, r d phi dz, right? Now what is volume? Volume element is equal to, see, look here, volume is equal to this small volume, this area into height, right? Area into that height, okay. Then what is this area? Area already we got r, this area r d phi dz, r d phi dz into what is height? So by considering this as the area, its height is this dr, right? So this is the height, so that is dr we already chosen, that is dr, right? So volume element is equal to r dr d phi dz, alright, r dr d phi dz, alright. Then this is volume element, this is area element, alright. Now to know this increment representing this areal and volume element, let us integrate this, right? So for the confirmation, see what we taken here, r dr d phi dz and r d phi dz, right? So let us go to a plain board, alright. Now see what is the volume element I got, r dr d phi dz, alright. So if it is volume, you know the cylinder volume is pi r square h, right? Pi r square L, right? So that small increment volume, if I integrate this volume, this small increment volume, then I should get the complete volume of this cylinder. Alright, so let us do. So if I am integrating here, integrate this side also. Here we can give limit. This R is varying from 0 to R, right? So that is RdR, and phi limit you know that is varying from 0 to 2 pi d phi, and Z you know that is the length of the cylinder, right? Then what is this? Maybe the length is small l, we can give small l. This is R square by 2, 0 to R, and d phi is integration phi, and limit is 0 to 2 pi, and dz is z, limit is 0 to L, right? Then R square by 2, I am giving the limit R, this is 0, then R square by 2 minus 0, R square by 2 into, this is 2 pi minus 0, that is 2 pi, here L. Then 2 to cancel, pi R square L, right? So we got the volume, right? So in a cylindrical polar coordinate system, this is the volume element, right? R dr d phi dz. Okay. Now let us see what is areal element, right? Areal element we seen, you know that that is R d phi dz. Now when find the curved surface area of a cylinder, you know that value, that is 2 pi RL, right? Curved surface area 2 pi RL, alright. Now let us substitute, integrating on either side. What is area? R square by 2, R we can take out, alright. R is not changing, right. Now d phi, because no increment, d phi is varying from 0 to 2 pi, that is d phi. Dz is varying from 0 to L, that is dz. Then R into d phi on integrating phi, limit is 0 to 2 pi. Dz on integrating z, limit is 0 to L. Then R into 2 pi into L, that is 2 pi RL, alright. So we got the area. Now this whole areal element, volume element, where we are using, right? You know, in electrodynamics, suppose a spherical charge distribution, charge is distributed inside a cylinder. Then they may give rho value, some R square sin phi z, right? Then this is representing a cylindrical charge distribution, right? If a cylindrical charge distribution is given, right, then to solve the electric field, right, you know that del dot E is equal to some rho by epsilon 0, right? So to find out this rho, to solve this rho, we need this cylindrical volume density, charge solving, because you know charge is equal to dq by dv is equal to what? That is our volume charge density, right? Rho. Then what is dq? dq is equal to rho dv. But this rho is given in terms of R phi z function, right? So we substitute that, then corresponding volume element, you should substitute this, right? So in electrodynamics, this coordinate system is very important to solve the different kind of charge distribution, field solving, potential solving and all, right? We study there, right? Alright. Now let us go back. Now see, as we seen, this areal element is r d phi dr or r d phi dz. See, look here. Here, if you choose, mainly we use this area. This area only we mentioned. If we discuss this area, right? This area r d phi dz, right? Length into breadth. If I choose this area, what is this area? This is dr. This is what? R d phi. R d phi. Then this area we can project it like this, right? So this direction is z cap. This area is r d phi dr z cap. This area projected like this. So this area is r d phi dz. It is along the radius radially outwards, right? So r d phi dz r cap, right? Alright, so that two area is given here. Alright. So this two area element is given and volume element also given. Alright. Now we have one more coordinate system, that is plane polar coordinate system, right? So in plane polar coordinate system there is no volume element because that is a plane, right? Only two coordinate x, y. If x, y is z, then only volume is there, right? So in plane polar coordinate system, you know that suppose this is our x-axis, this is our y-axis, then x, y. Suppose a particle, this is the position vector, you know, then what about this x? This coordinate is, if this angle is phi, then this is r cos phi and y is equal to r sin phi. So in polar coordinate system, what is x? R cos phi. What is y? R sin phi. Now suppose this is our r vector. Now I am increasing. This is my r vector. Now by increasing the r by a small amount dr. Alright? By a small amount dr. And this phi. This is my phi angle. I am increasing this phi by a small amount d phi. Then what is this? This is arc length, that is r into d phi. So this is arc length is r d phi. So this is parallel to this, then this also r d phi. Then here one area is created by increasing this dr, and so this phi is increasing in this direction, right? From here to here by an amount d phi. Alright. So this is our phi, right? This is our d phi. So by increasing this d phi and increasing this dr, a small area created here. What is that area? That area is equal to length into breadth. That is, that dA is equal to r d phi dr. Alright. R d phi dr. Now you know that, so if I consider this small area, suppose I consider this plane polar coordinate area fully, what happens? I get a circle area. You can check it, right? Because here if I take the integral of this, what is area? R dr. Alright, on integration r square by 2. Then this is varying from 0 to r. D phi on integration, that is phi. Alright, 0 to 2 pi. That means here r square by 2 into 2 pi. 2 to cancel. Then what I am getting? Pi r square. Then I got this complete area, right? So that circle area. Alright. So in plane polar coordinate system, x is represented by r cos phi, y represented by r sin phi, and ds is equal to r dr d phi. Alright. When which situation we use? Suppose some disk, right? So disk is a plane, right? So there is a charge distribution given, right? What is then surface charge density? How I can define sigma, right? Surface charge density I can define as sigma. Sigma is equal to dq by dA, right? Now what is dq? dq is equal to sigma dA, alright. So to find the full charge, right, q, I have to integrate this sigma dA. But sigma is given some sine square phi into r. It is a function of phi and r, like this given. Then we substitute here for sigma this value, and dA, then you have to choose this element, alright. Then only you can integrate, because our charge distribution, surface charge density, that is given in plane polar coordinates. Then the area element that you should select there is, that is area element in plane polar coordinates, alright. Alright. So up to this we see in different kind of coordinate system. We studied initially Cartesian coordinates, then we studied spherical polar coordinates, now today cylindrical coordinates and plane polar coordinates, right. Now previous lectures we seen some operators, divergence, curl, gradient and all. Now how we represent these operators in different coordinate system, okay. Though that will be discussed in next class, okay. Thank you.